So I'm going to go ahead and make sure that I record this one as well. So if anybody has any quick questions about the class, even homework from that last section that we went over, the very first section, 3.1, now is the time. Otherwise, I'll go ahead and start in on the next section of notes, which will be on 3.2. So any questions from anyone?
Could you go over, I think it was the 3.1, the video or the homework? Let me pull it up real quick.
Okay. I will do the same. And you're looking at the video assignment?
It was a homework, question number 6, I believe.
Was it a square root function?
Yes.
Okay. Go ahead and share my screen so you can see it. I have mine to where I can see all of them. Yours is usually just one at a time, I believe, but yours may also look a little bit different. Again, the numbers will be changed around, but the concept should be the same. Let me unhighlight that so you can see it a little bit better. Was that the one that you're looking at?
Well, mine was a bit different, but it's the same concept like you said. But yes,
Okay.
it is.
Okay. And you're okay with me going over that one?
Yes.
Okay. So we got f of x equals, and I'll share my screen once I have written this down, and you tell me which part, A, B, C, or D, so to speak, were you having trouble on? Was there any in particular, or just kind of the whole thing?
Just the whole thing in general. I tried watching the video and looking up videos, but I just couldn't get it.
You got it. You got it. So remember, we did something like this in class if you were there on Tuesday, where we are going to be what is called evaluating a function. And no matter what the function is that they give us, we should be able to evaluate or plug in basically whatever they tell us to replace the variable x in this case with. So there is our problem that you had some issues with. And remember, the reality of it is we should be having blanks here and here. It's f of something we know is equivalent to 1 plus the square root of that thing added to 27. So all you have to make sure that you understand is that we're not going to do f of these things individually, one at a time, in replacing wherever there is an x. So in reality, that -4 there would look like this. Do you see that?
Yeah. Wait, didn't you have to solve it? I thought you have to solve it, not plug it in.
Yeah, so good question. That is a little bit different than what you're saying and what they asked us to do.
Oh, okay.
So evaluate versus kind of what you mentioned, solve it. Sometimes they say let f of x equal -4. Now what are they saying is equal to one another? This whole thing and that whole thing, these are equal, which means I could then replace this whole thing, which I know is equivalent to this, with -4. And then, like you said, I would go through this equation and try to solve for the x. See the difference?
Yeah.
This one, they told us to replace the x with a -4. And since this is not the only place where we see an x, we replace the x with -4 everywhere. Does that make sense?
Yeah, it does. Okay. Well, I mean, I understand it now, so I should be able to solve it.
Perfect. So as I mentioned, the only thing that they can do, as you said, which is a good point, what if they said this and then ask you to solve for x? Well, then that's a little different. Now they're not giving us the x like they were here. Now they're asking us, remember we said f of x is equal to the y value? Now they're giving us the y value and asking us to solve for the x. Do you remember doing that in the notes on Tuesday?
Actually, I wasn't there for
Okay,
the.
perfect. I wasn't sure who was there or not, but yeah, great question. Anybody else got anything real quick? And I want to make sure I got your name right. Is it Elisa?
Yes.
Perfect. Anyone else? Anything from homework pertaining to how the classes run? Anything you need some help with? All right, then we will go ahead and start in on the next two sections, which for us, the first one is 3.2. So we talked about functions and we introduced functions in 3.1 and what made something a function. We talked about that vertical line test and then the horizontal line test to see whether or not it was a one-to-one function, meaning not just left to right, but also right to left. And as you can see, I mentioned to you guys last time, for those of you that were here, having a vending machine and you choosing A4 or G6, whatever that thing was that you want, whether it's candy or chips or some drink, right? Well, then you put the code in and you expected that one thing that you wanted to come out. And if that machine is functioning, then that one thing you put in should give you one thing out. But if it's a one-to-one function, then that means, what if you went the other direction? Which is what a lot of you probably did first. You peruse through and you look through the glass and you're like, ooh, I want that sports drink. That's what I want. And then you worked backwards and you said, well, what do I have to input to get that one thing out? That's what we mean by one-to-one. It goes both directions. One thing is only going to yield the other, whether you go right to left or left to right. Okay, so we're going to talk about those inputs and those outputs in more detail now. And remember the fancy term we gave for the input was domain. In range, those were all the outputs. And for us, when we're talking about functions, that's typically the f of x in equals y. Okay, so I don't know if you guys remember interval notation when providing lists or solutions even. We had to make sure that we knew that when there was a bracket involved, it was included. And when there was a parenthesis involved, then it was like an endpoint where it was not included. Right? So they give you a little example there. You guys can see that, but hopefully remember all the different variations of this because there's a lot of them. Okay, so here is the different types of ways that we could write this. The inequality written here on the left column, and then what the corresponding interval notation would be for that, along with the visual geometrically, the graph of it. Okay, and then even the words. So if we said that our answers, our solutions, where x had to be greater than some number, a, anything, then what we would say is, well, if you look at this, we have either an open dot, some books would do, or an open parenthesis, letting you know what, not a, but everything greater than it, everything to the right, right? Or everything less than a. So again, not a, whether you draw an open dot saying not that value, but all of these other values. And if you draw in every single dot, you notice that it just forms a line. And we put that arrow at the end to make sure that you know it continues on forever. Okay, but what if we wanted to include that value? What if it was a part of our solution set? Now remember, we like to read left to right. So when we're looking at this, we're not going to hit any values until we get to A, but not including A. And then everything to the right of it. So that's why this one is A, comma, to infinity. But I wouldn't want you to put it here and just say, well, it's A, but then to negative infinity. We're still going to read this from left to right. So that means we're starting to hit our values at what value? What does it start at?
Starts at A.
No, actually careful. And that's why I wanted to bring this up. Well, what does that arrow mean?
It goes on forever.
To the left. And you know, to the left, when is that going to end? Well, it doesn't. And since it doesn't, we had to come up with a symbol so that we knew exactly that scenario is occurring. And those are those infinity symbols. Now, obviously, the number 0 splits the positives from the negatives. So that's why this would be positive infinity and this would be negative infinity. So I've been putting air quotes around start because where are we starting on this? Well, we're actually starting to the farthest left that you can think of. All right. Like Beyonce said, you know, to the left, forever. So that's that negative infinity that we're quote unquote starting at. Okay. But you can never include an infinity as a solution. So that's why you'll always see parentheses around every infinity symbol. But you can include a value like A or B. Okay, so make sure that you know and understand the difference in what is called interval notation. And I don't care if you use the parentheses or brackets, or you used open dots and closed dots. I'm fine with either. They represent the same thing. Okay, any questions on any of those? Lots of different variations there. If you wanted to take a snapshot of it, there's all of them together. All right. Interval notation, we'll talk about that much more as we continue to press on. So next, we want to talk about how to provide the domain, all of those values that we could input. And so what we're looking for whenever they ask for us to identify or provide the domain, they want to know all the input values. Now, there's a lot of numbers. I don't know if you guys realize, but there are actually an infinite amount of numbers just between 0 and 1. An infinite amount of numbers just between 0 and 1, let alone going all the way to infinity. How can I prove it to you? It's very simple. What if I had 0 to 1 and I listed that? Say it's a foot or an inch or whatever we're dealing with. What if I took that and I asked you to cut it in half? Well, then what are you going to be left with? You're going to be left with the other half. Well, then what if I asked you to take half of that? You're going to be left with a half, and then half of that, and then half of that, and then half of that. What happens when you always take half of something? What are you still left with?
The other half.
Which means you'll always have something, and it will never actually be 0, even though we will get closer and closer and closer and closer to what? Having nothing. We call that approaching a value, which the fancy math term, for those of you that remember or have seen any calculus, it's called a limit. Okay, it's what it's approaching, not what it actually will ever be. Because we're going to get so close to zero, we're going to say, you know what, it's approaching zero, even though we'll still end up with that little bit of half each and every time. Okay? My point in all that is, if there's an infinite amount of numbers just between 0 and 1, how are we going to identify all of the possible things that we could put in, aka the domain? Well, we're not. What we're really going to strive for and try to find is any restrictions for our inputs that we would have to therefore exclude from the domain. Okay, and of course, what are they going to want us to put it in if we can? Write that domain, give me all those input values in what is called interval notation or interval form. Okay, so there's a few things that I want to make sure that you know, especially in these circumstances. When you see a fraction or a rational expression, we call it, and they ask you to find the domain, then I want to, step one, find all those values, but I need to identify the restrictions. And what do we know that we cannot have in a fraction?
You can't have a 0 as the denominator.
Very good. No matter how many things I have on top, I cannot divide it 0 ways. I can have nothing and divide it any number of ways I want. That's still going to be 0. But I can't take any number of things and divide it 0 ways. That makes no sense. Okay, I can prove it to you very easily. It's a simple way to show you if you don't know what the answer is. If you didn't know what the answer was, all you do is multiply over both sides by that number, and that will get rid of the number. And we get 0 is equal to what times our number? 0. That's the only thing that would work. So that's our answer. But if I try to do that over here, I'd be multiplying by 0 to both sides to cancel this out, even if we could do that. Watch. 0 times what number gives you some number? Well, nothing, because we know 0 times anything is going to give us the 0. So again, that's one of the quick, easy ways to show you that you cannot take any number and divide by 0. It does not exist. So that is why we have to take, for our restrictions, and we got to take the denominator, and we got to set that denominator equal to 0. That will tell us what the restrictions are for the domain, which means what does work. Everything else. Those are the only restrictions. Okay. Now there's another case that happens frequently as well that we want to make sure that we highlight and mention, and that is if our equation, our function, has an even root. Then we want to make sure we set whatever's underneath that radicand, that radical, to be greater than or equal to 0. Because just like we can't divide by 0, we can't take square roots or fourth roots or any even root of a negative. So that's why we set it to greater than 0. Hopefully that makes sense. There it is for the even root. If you guys wanted to have it separate, I like them both together a little bit better. Don't have to do as much. One other thing I want to make sure that you know is sometimes when we have those open dots versus closed dots, those parentheses versus brackets, sometimes there's going to be a jump, a skip or a hop on our number line for our solution set or our domain or whatever it is the question that they're asking. And we need to use this weird looking U symbol called the union in order to combine one side of our number line and another. Okay, so let's take a look at what I'm talking about here. See if you can give me the domain represented or the solutions of that number line. Go ahead and give that a try real quick. Now, don't forget, we like to read from left to right. So where should you be starting this as you look? What does that arrow mean? Where are we starting?
Negative infinity.
Very good. And are negative or positive, are infinities ever included in our solution set or our domain if they're asking for it?
No.
Very good. You can't plug in infinity, right? It's just an idea. Some of you guys are putting it in on the chat. Very good. So I'm going to always put a parenthesis around a positive or negative infinity. We're going to put a comma to represent everything else, but then I have to go all the way till what value?
-2.
Very good. All of these are accounted for. Is -2 included?
Yes.
Yes, it is. So we're going to give it a nice big hug and include it as well. Give it the brackets, but you can see there's a little void here, isn't there? There's nothing here that we want to be included in our solution set or domain or whatever it is, the question that we're working with. So we need to unite the other solutions, which starts at what value? And is that included?
Yes.
Because it has a solid dot, just like every single one of these that are so closely pushed together all form a straight line. But all of those solution sets or domain, our input values, go all the way up to what value?
3.
And is that included?
No.
So we put a parenthesis around it. You guys remember doing this? Do you remember when you often had to use this interval notation when you got a bunch of different solutions or answers? It was usually when you were solving inequalities, the greater than or less than symbols. Okay. Well, then what if I gave you a different graph that has both X's and Y's, not just the X-axis involved? And I'm not only going to just tell you interval notation on this one, I want you to do set builder notation, and I'll explain what that is in a minute, just so that you know and recognize we almost always put interval notation down. It's easier. Even though there's a Y values that are now included on this grid in this graph, I still want to just focus on my input values, my X's. Because if I know where the X's go from, then I could figure out where the Y's would go from. Okay, so let's give the interval notation for the domain of this. what would the domain be for interval notation of this function f, they're calling it? Good, seeing some good stuff in the chat. Where are we going to start? Very good. A lot of you are putting -3. Now there is an open dot, so is that included, that x value?
No,
Good. So we're going to put parentheses, but are all of these x values included on my grid, on my graph? Good. All the way up to what value?
1.
And is that included?
Yes.
Because it's solid. How come it doesn't go to infinity? Which is what a lot of people would put. Or 2, as some of you were putting in the chat. How come it stops at 1? Because what is at the end of this?
Solid dot.
Which a lot of people won't even put the dot. They'll just keep drawing it, right? They won't even put all these and know that these are all points or dots. They'll just draw it like this, but then you're going to have that there. Otherwise, if you don't, you're including that -3. You're including this, which means it also really matters if you put this or that, doesn't it? Because again, some of you guys will only put that right there. Oh, I go from here to here because that's the window that I have. That's it. That's all I can see. If you don't put the arrows, it means a lot. Just like if you do put the arrow, it means a lot. It means it keeps going down and out forever. But for us on this one, that would be the domain in interval notation of this function f. And how do we know it's a function?
It passes the vertical line test.
Very good, Will. Vertical line tests. Is it a one-to-one function?
No.
No.
Very good. Fails miserably. 1, 2, 3 places it actually hits. Could you make this a one-to-one function? And that's a tricky one. I know a couple of you are saying no in the chat. Yes, you actually can. And the way that you can is by restricting some of it and saying, you know what, this is my whole function, but I only want you to use the x's that are greater than or equal to 0. Because if I tell you to use this function, but only from 0 and on, now do you see it would pass that horizontal line test? So that's why I chose 0 in particular, because if I chose -1 and I got rid of all of this side or the other, still fails. Okay, and that's going to be an important concept for us down the road when we talk about finding inverses. So I just wanted to quickly mention set builder notation, which means that we are going to build a set of values. And what are the values that we're finding? Well, x's. Could be y's, just depending on what they're asking. Could be some other variable, but we're going to say, you know what, pick an x such that we're going to just draw this straight line to represent, hey, here's how you can build this set of numbers that would be your, in this case, domain. And we would say, well, what could x be? X could be anything such that as long as we are to the right of -3, which how would you say to the right of -3 in math symbols? How about that? Does that work? What does that symbol mean?
Means any number, or x will represent any number greater than -3.
And wouldn't that be anything this way?
Yes.
Do I want anything and everything this way though?
You're gonna want to stop at 1.
Good. So I also want to let you know, hey, x can be greater than -3, but I also want x to be less than or equal to the 1. And so that I don't have to write this twice and put weird symbols in there, I'm just gonna, since this x and this x are the same, I'm gonna squeeze them. And I'm gonna say, you know what? X had to be greater than, which if I'm facing open towards the x, that means greater than the -3. You guys see that? My x had to be greater than -3, but less than or equal to the 1. And that is what is called set builder notation. X such that your x is greater than a -3, but less than or equal to a 1. Do you guys see why we use interval notation? That's a whole heck of a lot easier, isn't it? Just pay attention to moving left to right on your grid. Or if it's talking about the y's, we'll go bottom to top. It's always smallest to biggest. And then parentheses versus brackets. Open. Looks like an O. Parentheses. Closed. Open versus close point. Okay, hopefully you guys remember that, because now I want you to go ahead and find it without the graph. Let's do it algebraically. What if I wanted you to find the domain of this, what is called a ratio or rational function? Help me out, let's do it together. How would you do that? What works? What's the domain? Good, somebody put X. We're looking for all the things that we could plug in for X and get something out once we do all this for our Y. Are we gonna sit here and check everything? No, we can't. Remember, there's an infinite number of things just between 0 and 1. We're not going to be able to test them all. So what are we really looking for?
Restrictions.
Good. The things that don't work, those restrictions. And in a fraction, what did we say we were restricted to knowing how to do? We didn't know how to divide by 0. So we know what's going to work. A lot of things, everything in reality, all real numbers. This double-legged R stands for real numbers. Except X cannot equal what value or values? Solve that equation. Add the 1, divide by 2. Hopefully you can even do that in your head. We know that X cannot equal 1/2. And I'm fine with you writing it like that. If they ask you to put it in interval notation, what would you have to do? What does work? Where would we start? All the way left. Very good. Negative infinity. Some of you guys are saying in the chat, all the way up to what? Very good. That 1/2 that we said was our restriction. Is that included? Should I include that 1/2?
No.
Very good. No, that's the one and only thing we said cannot be part of our domain. But we need to unite the whole other side of the 1/2. So we will not include, but start at it and go to the positive infinity, the right of it. Excellent. All good there? I'm good with either. Just make sure that if they specify in the instructions, you answer the way that they want, because I want you to get your full points. The understanding is there for either one of these. How about the domain of a radical? What do we say we don't know how to take the square root of? We don't know how to take the square root of negative values. So how can we ensure that we don't get a negative? What does that mean on our number line? It would have to be greater than what?
0.
Or equal to. Very good. Anything less than 0? Negative. So I want to take whatever is under this and make sure that it is non-negative. And that's the way that we do it. We say that it would have to be greater than or equal to 0. And should you know how to solve that? Absolutely, you're in pre-calculus. Okay, so subtract the 5. Now I got 2x greater than or equal to -5. Lastly, divide by 2. And you will get an x that's greater than or equal to -5/2. So you can say all real numbers except, right? You'd have to make sure that your x is greater than or equal to -5/2. Or if you wanted to write it out in interval notation, that would be from where? Where would we start? Well, we just went through and solved and said it had to be anything that's greater than or equal to this. And if you think about your number line, if 0 is here and -2.5 or -5/2 is here, we wanted it, could be equal to, and everything greater. That's what this said, right? So am I starting to hit out here at -infinity for my solution set? No, very good. Not until I got to what?
-5/2.
And everything to its right, everything greater than it as well. So -5/2, including it to infinity, never include the infinities. Either way you want to write it. Is this all coming back to you a little bit? Trying to go nice and slow at the beginning here, okay? Now, you should be able to list both the domain and range for all of these basic functions that we're going to be talking about, okay? In this book, they call it the toolkit, because you should have those tools as an easy kit for you to just look up, use, memorize off the top of your head. Okay, I want to make sure that you guys know the domain and range for every one of our basic functions. So next week, we'll get into it a little bit more detail about what the graphs of these look like, because if you can visualize what the graph looks like in the top of your head without doing anything, that's going to help you. It's going to pay dividends, not only in this class, but the following. Okay. So wanted to mention that now. We'll talk about it more. There's one more piece to this first section for today. No pun intended. It is called a piecewise function. right? I don't know if you guys recognize this right here, but this separated into two parts or pieces is the absolute value function. Because if any one of you gave me some value for the absolute value, right? Give me a number. What's your favorite number? Okay, 4. I see the absolute value of 4, right? I know the answer to that is 4. But what if I asked you for the absolute value of -4? What do you get?
4.
Now, if you plug in 4, you get out 4. So in other words, you're going to get out exactly what you put into that thing if it's what kind of number? Non-negative. I can't just say positive because 0 is included in it, right? But if x is less than 0, which means it is negative, then what are they saying is going to happen to the thing on the inside? What are you going to get out? You're going to get out negative whatever you put in, or what we call the opposite. Because if you put in a -4, according to this, doesn't it look like it says that you should be getting -4? But in reality, it's saying if you put in anything, you will get out one of two things, either that thing or the opposite of that thing, depending on if it's 0 or above or less than 0. So according to this definition, it's saying that, well, whatever this A is, if A is equal to 4, then you're going to get out your A. But if A is equal to -4, it's saying you're going to get negative your A. And what happens when you take the opposite or a negative of a negative?
Makes it positive.
So that's where this definition gets really confusing, because people are like, whoa, 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 whoa. I know the definition of an absolute value. I always get out positives. And this is saying I'm going to get a negative out. No, no, no. It's saying if you put a negative in, you're going to get the opposite of that negative, which, as somebody mentioned, is going to yield a positive value. Okay, so piecewise functions can look very simple, but can challenge you like this, or they can be a little bit more extreme, like something like this. Now, how many pieces do we have to this one function? Very good. 3. 1, 2, 3. And each has a rule. You will only use this for your function if this is true. You will only use this as your function if this is true, and so on. So what I'd like you guys all to do very quickly is try to graph this, what is called piecewise function. Right? So I'm going to stop it for just a couple seconds here and give you guys an opportunity to try to graph this. Go ahead and start. All right. Let's see how you guys did. Now, this does require a little bit of knowledge of how to graph certain functions, like a cubic, constant, and square root function. So hopefully you remember a little bit about Hopefully all of those, if not some of them. Okay. Now you can do this in any order. You just got to make sure that you know that these are the keys. These are the most important parts because that's what depends on what function we're going to be using for each. All right. So you guys want to do this left to right? Is there one that you want to do first in particular? How'd you guys start it? The blue one in the middle. I agree, Ezekiel. That's a good one to start with because it's very simple. It tells you that y is going to be equal to -2 everywhere. It doesn't even depend on x and what you're going to get out. Your y is always going to be -2 as long as you are between -1 and 4. So I'm going to go and I will use blue for that. -1, 1, 2, 3, 4 is there, and 1, 2. So I know from here to there, I'm going to have, now should I have closed dots or open dots there? Or does it matter?
Open dots.
How
Both
come,
ends.
Will? You said on both ends. How come, Will?
There's no greater than or less than, or I mean, equal to sign on both of the arrows.
Excellent. Again, pay attention to details, guys. This is going to save you in calculus. That's where most people make mistakes. And those calc problems can get very, very, very involved and long. So you want to really make sure you pay attention to those details. They did not have the equal to those. So that means we will have an open dot, and I'm going to exaggerate, open dot, and then everything else from there to there. Okay, I'll go ahead and make my line a little bit thicker for the graph part. All right, cool. We got that one taken care of. Now what?
So you have the on the 2 for the y-intercept. It says -2, so I don't know if it's supposed to be like below the x-axis or it's supposed to be above.
Does it matter?
I believe it does. It says -2 for a
Yeah.
reason.
Very good. -2. Excellent. Glad somebody said something there. Right after I get done telling you to pay attention to details. -2. Excellent. Now what? Red or green? Do you guys remember how the cube graph looks or the square root function? Okay, let's start with the square root function. You guys know how to take the square root of certain things, right? And again, if you ever don't know, you can always go ahead and plug things in. I know the only thing that I can take the square root of are perfect squares, like 0, 1, 4, 9, 16. I know the square root of those. So if I wanted to plot some of these points, then I should be able to. The 0, 0, the 1, 1, the 4, 2, 9, 3, right? Hopefully you remember the graph of this. Looks like a half of parabola on its side. Now, if you don't want to graph the whole thing, that's fine. I get it. Because we're not going to end up using the whole thing, are we? Because this one said only where x is greater than, strictly, to 4. Make sure that you can see that there's no equal to there. Which means I'm going to go to the 1, 2, 3, 4 value, and I'm going to put a what there?
Open dot.
I'm going to have another open dot, and then I'm going to get rid of the rest of this piece. All right, now that looks kind of ugly, so to clean it up, what I would do is probably erase some stuff. But if I do that, it's going to erase the whole thing. Right? So again, I would go to 4, 2, and then I would draw the rest of my drawing. That was not a very good one. half of a parabola on its side. Okay, we will go ahead and leave off the rest of this. That part is not even part of it, right? But just so that you can see the half of a parabola on its side. So we got all of this, we jump down here to this, and then we need the left portion over here, which they said less than a -1 is going to be a cubic. And again, if you don't remember what the cubic ones look like, go off to the side and plot some points for it. You should definitely know 0, 1, 2 cubed is 0, 1, and 8, or even -1, -2. There's some values. And hopefully you remember, if I plotted those points, I kind of get that elongated S shape. You guys remember that at all?
Yes.
Great. So -1, -1, I'm going to lightly put that point, -2 all the way on down here to -8. I'll plot that point. And then again, the 0, the 1, the 2, and the 8 all the way up there. If I wanted to lightly draw this, I could. Am I going to use that whole part of that function?
No, just from -1 to -infinity.
And is it open or closed? What are we doing here?
Open dot with an arrow.
Good. So I'd get rid of all of this, right? And I'd have an open dot at -1, -1. And then we would have to have that arrow going down that direction. So to kind of clean this up, get rid of that, get rid of that, and draw this. And guys, all of this together, which is why I circled it in pink here, this is my f of x function. See why we call it piecewise? It's put into several different pieces. Now, by the way, is this a function? You should all know, absolutely, yes, it is. How come it's a function? They told us it was a function. Not only in words, by saying piecewise function, but also as a symbol, writing it as f of x, a function with x's in it. Why did some of you say no in the chat? Because you're thinking, oh, it didn't pass that vertical line test. Oh, yes, it did. That's why it's so important whether or not you have open or closed dots. Would it still pass there if I had a closed dot there?
If you had one closed dot.
Only one. Very good. All out here, obvious. You can see that. All in here, obvious. You can see that. But this point right here and this point right there, because there is that overlapping using those values, was important that one was open and one could have been closed, even though it wasn't. Okay. So I'm going to give you guys a couple minutes break. We'll come back. We'll do the last section for today, and then I'll give you guys the rest of the time to work on the group quiz. Cool? All right, welcome back. As you can see, this is a very important, not just for this class, but even for your calculus course that you guys hopefully will be taking next. And it is called rates of change. And then we're going to look at some of the attributes of graphs. Okay, so this is something that you're going to do a lot of in Calc 1, right? So that's why I put it's super important, not just in math, but also in calculus. So this is stuff that you're actually really, really familiar with. You probably just never heard it called this before. This is called a rate of change, right? This is the formula for it. Now, this is the fancy math symbols that we use. It's actually a Greek letter called delta, but it's like a lowercase d, right? So it's like a dy over a dx. And what that stands for is the change in our y values over the change in our x values. Have you guys seen something like that before?
Oh, yes.
In what? What is it called? Do you remember what that's from?
I remember I saw it on Precalc, but I'm not quite sure.
Does that give you a hint?
Back from 7th grade. It's on the tip of my tongue.
Yes, very good. It was from when you first started learning algebra. The very first graph that you learned to put onto paper was that of lines. And so you had to learn the slope or the steepness of the line, how the line changes when you're talking about your X's versus your Y's. Guys, I don't know if you see it, but this is just our y2 minus y1 over x2 minus x1 slope formula. In a lot fancier terms. And not only are we going to just not pertain to X's and Y's and talking about the slope of a line, we're going to talk about the real world and how this can be what is called a change of rate or rate of change. But all I want you guys to see as something that you already know from, yeah, like 7th grade. That's just your slope formula. Okay, but we're going to apply it in a different form. That's all. It's going to represent something different. We call the average rate of change. Okay, super important. So as I already asked, what does it look familiar to? Slope formula, which we used m for representing the slope, and then the change in our x's and y's. The rise over the run, we said. So how can we take this slope, x's and y's, in algebra only and pertain it to real life? Well, I actually had a class on campus today, first one in almost 2 years. It was crazy. We were all masked up, but 8 a.m. we were there. Okay. I rode my bike. Are you guys impressed?
Yes.
Yes.
You shouldn't be, because I left yesterday. No, what's my point? What if you don't know that I actually live right across the street from Fresno City? I live in the tower right over there. Are you still impressed?
Yes.
Yes. It's cold outside in the morning.
You're like, yes, I don't know how to ride a bike, Alan. That's awesome. I got to have the 3 wheels. You know what I mean? No, I mean, there should be some other things that would make it more impressive. So yeah, if I said I was leaving from my house to Fresno City, and let's say it was 20 miles away, and it took me, let's say, 2 hours to get there. Now you can make your impression felt a little bit more or less based off of more information. So if we look at this, what could you tell me my rate, the speed that I traveled from my house to Fresno City, what was it?
10 miles per hour.
Okay, well, what does that 10 miles an hour represent?
It means for every hour that you were on the bike, you rode 10 miles.
But does that mean I actually went 10 miles an hour as soon as I jumped on my bike and then all the way up till I got to Fresno City College?
No.
No. What is it?
It's the average speed.
That's right. So you can get the average rate or speed that you traveled if you know an ending and a beginning point. Just like that slope formula. I could say that this was 0, 0. Right? Time 0, mile 0. But then here, it was what? 2 hours traveled in that 20-mile range that I had to go. And if you guys can see that, now would allow me to take my 2 points, just like we always have, and now I can find the slope of it. I can call this my x and my y, this my x and my y. Call this x1, y1, my second point, x2, y2. And I can take the like things and find the slope. It would be the 20 minus the 0 for miles, and the 2 minus the 0 for hours. And we would get 20 miles on top, 2 hours on bottom, which, as Will and a few others were saying in the chat, would give me a simplified version of 10 miles per 1 hour. And we abbreviate that big ratio or fraction with MPH, miles per hour. Does that make sense? But again, remember, that is my average rate that I traveled. I did not go 10 miles an hour the entire time. That's just the average. So, my friends, word to the wise, there's actually places throughout the country that use this simple mathematics, and I mean simple, 7th grade we're talking here, as some of you mentioned, to give tickets, speeding tickets, between toll booths. Because what do they definitely know? What can they tell between the toll booths? Say they're 50, 100 miles away. They know that distance. And what else do they know?
The speed limit that they posted.
And when you put your ticket in and you put in your $2 or $3 or whatever, you pass through in the fast pass lane, they know your time. And then they know your time at the other one. And guess what? If it's before that time, what did you have to do?
Speed.
Simple mathematics. Pretty cool. So let's make it look a little bit more mathy. Let's see if they asked you to find the average rate of change and they gave you some nasty old function and they gave you some interval, 2 times, if you will, that they wanted you to find that average rate of change. When you see average rate of change, what do I want you to see or think of? It's just a slope. That's what I want you to think of. It's the slope formula. And they gave you 2 x's. Here's my first, here's my second, in interval notation. So I already know that I'm going to do y2 minus y1 over x2 minus x1. And of that stuff, what do we already know? My x values. What's the only thing I'm going to have to work to get?
The Y's.
That would be wise. Very good, Will. And as long as you're consistent, you'll be fine. I'm going to go to my function. I'm going to plug in 9. I'm going to go to my function. I'm going to plug in 1. And I'm going to find those values and then subtract them, which I can already do for my x's and the difference between 9 and 1. You guys with me on that? All right, then let's plug in 9. If we want to find f of 9, remember like we just did earlier when somebody was asking about a homework problem. If we're going to do f of 9, then that means they replace the x with a 9. Then you need to replace the x with a 9. So we would get 9 minus 2 times the square root of 9. And then we're going to do f of 1, which means 1 minus 2 times the square root of 1. And of this stuff, we should be able to take square root pretty easily, multiply it by that -2, and then add the 9 to it. So what is the square root of 9?
3.
Good, times the -2. So we get 9 minus 6, which is, some of you guys are already working the whole thing out in the chat. Very good. Over here, even easier because they're just ones. Square root of 1 is 1. Times that -2 is just -2. So we got 1 minus 2, which is, careful, a -1. I say careful because remember, you're trying to find the difference of these two values. We found those two values. Now we need to find the difference. And what happens when you subtract a negative in your life?
Makes a positive.
That's a positive thing. Okay. Remember, it's just the opposite. That's what that symbol means. So if you want the opposite of -1, that's +1. And what is 3 plus 1? Divided by 8. What does that 1/2 represent? Our average rate of change over this interval for this function. Again, on average. Okay, it's just the slope basically. So that's the first half of that section. Here comes the second. Let's talk about the attributes of graphs. Let's talk about the key things of graphs. What would you guys want to know about graphs? What might be some good things? Good, I like that answer in the chat. What they look like. What more exact? What kinds of things would you maybe want to know besides just the basic look of it?
Some X and Y values.
Good, some key points. I like that. Very good. How about where it's increasing, going up, and where it's decreasing, going down? How about high points and low points? Call them maximums and minimums. These are some of the things that we're going to talk about. If we were to have a graph like this, say, a cubic function. Hopefully you guys remember the looks of those. We'll review those next week. Okay. We're going to talk about what it means to be increasing. As, again, we read these, it's always left to right, smallest to biggest. As my x's increase, what are my y's doing? Well, they're increasing until a point, and then what do my y's start doing? Decreasing, getting smaller to a point, and then my y's start increasing again, indefinitely, forever. So again, you don't get to choose how you read this. We're always going to read from left to right. Okay, increasing, decreasing, increasing. But notice there's a key point, a critical point in both of those places where it changes from increasing to decreasing or decreasing to increasing again. Okay, and those are going to be key points for us to be able to find in calculus. And luckily in calculus, we'll find a much, much quicker and better way to find those values. Okay, but for now, we're just going to talk about them, make sure we recognize them, and then hopefully that if we can, the function is decent enough, we'll try to find some of these things. Other key points that we like to find is where our y values are equal to 0. we call these the x-intercepts because they intercept or cross through our x-axis. Okay, those high and low points are called minimums if they're low and maximums if they're high. I'll talk about what it means to be local in a minute. So let's go ahead and just mention that now. What is the difference between a local maximum versus a global or absolute maximum? Look at this graph. Does this graph right here have an absolute or global on the entire graph? Does it have a highest point?
That would that highest point be in infinity?
Good. Is infinity a point? No, very good. Infinity is an idea, right? Just like we said with the interval notation we were talking about, you can't include them. We always put parentheses. You can't graph infinity. It's just the idea of getting really, really big or really, really small. So since this has an arrow on it, is it going to have that highest point or a lowest point? No, very good. But locally, if you're a local kid, then that means that you grew up around here. Now, to some people, around means Fresno, Clovis, and that's it. To others, it means Reedley, Madera, Chowchilla, Kingsburg. The whole valley is local. Some people may even think California is local, right? So when we mean local, we just mean around. Whether it's that big around or this big around this value, it is by far the highest. Is it the absolute or global maximum, highest point or lowest point? No, but around it, it is by far the highest or lowest point, which is why we call it a local minimum or a local maximum. And why do we even care about those? What's important about those peaks and those valleys? That is where it changes from increasing to decreasing or decreasing to increasing. Okay, those are going to be very important for us to be able to find those attributes of a graph. Okay, so I kind of blew it up there for you so that you could see it's where it changes from increasing to decreasing, or if you flipped it, vice versa. Okay, but going from increasing to decreasing will always give you that local max. But if it's the other way around, decreasing to increasing, now it's going to be a local min. All right, you guys see the difference there? Good. We call those local minima and maxima. That's plural. Okay, instead of minimums and maximums. All right, but all of this verbiage here is exactly what I just showed you graphically. I think it's a whole lot easier to see via a graph than all these words. Right? So you can read through those if you'd like, and how we figure out whether it's an increasing or decreasing function. Right? And we can find those maxes and mins locally. By comparing our y values at certain x's. Okay, so let's do an example. And again, we'll start with the graph because it's easier to see. If I asked you to find the intervals, again, talked about that earlier, of increase and decrease. Increase and decrease. And give me the local max and mins. I'll give you a second to think about that and then see if you can give them to me. All right, who can tell me how many critical points are there on this?
I'm seeing 4.
4, where are they at? Can you tell me?
1/2, 2, and then the highest point, lowest point.
Where's the highest point and lowest point?
The lowest point is at 1, -1. Highest point is at 3, 1. And then at the x-intercepts at 2, 0, and 1/2, 0.
Okay. Very good, Will. You're very close. There are all important points that you listed, but these two aren't going to help me with this stuff. Those would help me to graph this more precisely, that I go right through that point and right through that point. But where is this increasing and decreasing at? Well, remember, let's start left to right. What is it doing way out here?
It's decreasing.
Very good, because remember, although this looks like it's going up, we are going from left to right on this ride. We're going to do this. So it decreases until when? Is it this point? Where it crosses through from my positive y's to my negative y's at that x axis? Good, no. So that's why I don't really care about that point or that point, our zeros, our x-intercepts just yet. Okay, I know it decreases on all of this until I get to that value. So I'm going to say it decreases starting at -infinity, comma, all the way up to what?
-1.
Actually, remember, we're going to just talk about the x-axis. We're not going to really worry about listing the y's, because that's what we're reading are the y values. What is decreasing? The y values are decreasing. And we're going to denote it by listing the x's from left to right, smallest to biggest. So it's actually from -infinity to 1. All of that is decreasing. And do we ever include infinities?
No.
So a parenthesis around it, should I include the 1? Some of you are putting yes. All right, let me include it for now. What do we do to the right of 1? What do our y values do as our x continues to get larger?
Increase.
Very good. It increases. So now we're increasing. From where? Starting at what?
Starting at 1, finishing at 3.
And should I include the 1? Some of you are like, yes, I'm Ron Burgundy. No, why should you be questioning yourself now? You didn't question yourself when you put it was decreasing and you included it there. Can it be decreasing and increasing at the same value?
No.
So should we just guess and sometimes put it decreasing, sometimes put it increasing?
At increasing and decreasing, they're both are not included.
Very good. Because it is the place where it changes from one to the other, that means we cannot include it at either. It's not increasing or decreasing at that point. Very good. Way to fix that mistake, everyone. Then, continuing on our X journey, as we increase, right? Decreased here, increased here for my Y values. Then at 3, it started to what again?
Decrease.
By a little, but it's still doing it until we get to that 4-ish, right? I'm just going to put 4. So we're going to not include that, and we're going to have to unite the other interval of things that are decreasing from 3, not ever including where it changes from one to the other, all the way to, we'll just say 4 to keep it easy. Again, not including 4, because now we need to unite the other things where it started to increase. And that was from 4, not including it, to what?
Infinity.
And beyond. Very good, Ezekiel. Buzz Lightyear, whoever you are. Now, how about the second part of this problem? They wanted to know the local max and mins. Do we have an absolute maximum?
No.
No, it just keeps going up and out forever. So no absolute max. Is there an absolute minimum?
Yes.
Yeah, very good. That is my lowest point. But they didn't ask for those just yet. I wanted to just start us off with the easier things, the locals. Around this point, it is by far the lowest. And notice I said this point. You can either give me just the X so that I have to then go find the Y, or if it's easy enough, just give me both. Where is the local min at?
It's at 1, -1.
Excellent. Because around this, it is by far the lowest point. Same thing around this though, isn't it?
Yes.
So maybe another one at 4 comma, I don't know, what is that, like 3/4? If it's not exact, don't worry about it. You guys can figure that out with calculus down the road. But then there's also locally a highest point. And that's at 3 comma 1. Now, one thing I want to make sure that you understand, these are points, ordered pairs, coordinates. These are intervals. Although they look the same, don't they? Just be careful. Make sure you answer what they ask in the form that they ask. Okay, so let's talk about that absolute or global maximum. What does it mean if it's absolute?
It stops or it doesn't keep going.
Very good. Over the entire graph, right? Globally or absolutely, it is the highest or lowest point. And as you mentioned, it has to somewhere stop, because if we have an arrow, it's going to go down or up forever. There will never be an absolute if that's the case. Right? So I'll give you a second to think about this one. Give me the local max and or mins. And then give me those absolute or global max or mins. Is this getting a little bit easier? What do you guys want to give me first? Locals? Can anybody give me a local max?
216.
216. I would agree with that. Any others?
Oh, negative 216.
Oh, very good. Also negative 216. How about local mins?
0, 0.
Excellent. Around this, it is by far the lowest point. Any other locals? What about these endpoints? Can those be local? If I circle around this, is it the lowest point? Or around this, is it the lowest point? Well, the problem is we don't know what happens on the other side of this, do we? Does it hit that and go back up? Does it keep going down? Straight down? We don't know. We don't know if this keeps continuing there or hits that and goes that way. So guess what? You can never have at an endpoint. Anything locally because you don't know what happens on the other side. But what does that mean you can have at endpoints? Doesn't mean you will, but can have.
You can have absolute maxes or minimums.
Very good. Is this definitely by far the lowest point on this entire graph?
Yes.
Yes.
And what does it appear to be at?
3, negative 10.
Very good. Is there an absolute maximum?
Yes.
Yeah, very good. There is a highest point. There's actually how many of them?
2.
2 of them. Very good. It would be at that value of 16 for both 2 and negative 2. Very good, guys. It's a nice start. That's all I got for you as far as notes go. Hopefully that made sense. It's just the beginning of some of these calculus topics that we will get into and learn better ways to find these things. Okay, we're just going to make sure we define them, understand them, start to learn how to find them, but wait until we have calculus to find exactly where they are. Okay.